All right, hello everyone, and welcome to my channel. This is an educational channel, and we try to look at different theories of everything and go into them deeply and, dig out what we can use and how we can use it. And, working on our own paradigm shifting and awakening to 5D consciousness. Today is our 485th video that we've done on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an engineer, American engineer, working out of Portland primarily, born in North Dakota in 1898. In 1959, he proposed his two fundamental postulates about how the universe operated. And then in the final 30 years of his life, he elaborated those two fundamental postulates into a theoretical universe. And he wrote some books where he compared his theoretical universe with the empirical universe that was measured and compiled by legacy scientists to see kind of how he did, or whether his theoretical universe matched up with the so-called actual universe. And one of those studies here is right here that we're working on today. It is a book called Basic Properties of Matter that he put out in 1987. And we're in the middle of chapter 11, Thermoelectric Properties. Now, if you want to get a more detailed description of the reciprocal system, please watch one of my first 474 videos on this topic. I've recently just stopped going over it because I really want to get into the text a little bit more, and it really takes like 20 minutes minimum to kind of sum up the reciprocal system to the point where a new listener can kind of follow along with the text. So go and look at one of those videos, and then you come back, and then you'll be prepared to go through. Now, you can just wing it and give it a try, see what you can pick up. I'll just tell you that the reciprocal system is also known as the universe of motion, and Larson was one of the few scientists to propose motion as the sole constituent of the universe, not matter or energy, but motion is the most fundamental thing. And Larson's first postulate, where his original ideas are encapsulated, is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So the universe is made out of motion. Motion is the relationship between space and time. Motion is a fraction, with space or time as the numerator, time or space as the denominator, with the caveat that motion, space, and time come in 3 dimensions, and they also come in only discrete units. And when he's talking about motion, he's referring specifically to a kind of motion that is actually more general, but he calls a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction, which you can envision using a balloon and put dots on it with a magic marker. If you blow up the balloon, all the dots will be moving away from each other, but they won't be moving in any specific direction. In fact, they'll be moving in every direction. That is a scalar motion, every direction outward. So every dot will be moving away from every other dot. That is that outward motion of the balloon is what Larson calls the progression, and this progression is really the source of all manifestation in the universe. So manifestation really occurs by taking that outward motion and reversing it and kind of reeling it in and harnessing it. And that is really how you get matter, basically turning that outward motion of the balloon to an inward motion of the balloon, where all of the dots will be moving toward each other. That's what he calls gravity. And okay, now we are in, again, just watch one of my first 474 videos if you want to get a little bit more complete description. And we're going to get into talking here about thermoelectric properties. He just gave us an equation here for thermal conductivity, K over Cp. That's thermal conductivity. I believe the K is a constant. I believe the P is for pressure. And I'm trying to remember what the C is. Conductivity. It is something, I think it's a coefficient of conductivity or something to that effect. I'm sure that Larson will clear this up as we move along. So let's just keep going. As we saw in the earlier chapters, the specific heat of the conductor materials follows a straight line relation to the temperature in the upper portion of the temperature range of the solid state. And the resistance is linearly related to the temperature at all points. At these higher temperatures, therefore, there is a constant relation between the thermal conductivity and the electrical conductivity, which is the reciprocal of the resistivity. This relation is known as the Wiedemann-Franz law. The relation expressed in this law breaks down at the lower temperatures, as soon as the specific heat drops below the original straight line. However, the failure of the relation does not occur as soon as would be expected from the normal specific heats of the metals, most of which begin to drop away from the upper linear segment of the curve in the neighborhood of room temperature. The reason for the extension of the high temperature linear relation to a lower temperature in application to thermal conductivity is that the specific heat under the conditions applicable to thermal conduction is not subject to all of the limitations that apply to the transmission of thermal energy by contact between atoms of matter. Instead of going through some intermediate steps, as in the measured specific heats, the effective specific heat in thermal conduction continues on the high temperature basis down to the point where multi-unit motion is no longer possible and a transition to a single unit basis is mandatory. The temperature designated as T sub 0 in the previous discussion, the point at which the specific heat curve reaches the zero level, is the same in thermal conduction as in the atomic contacts. But in the interaction between the electrons and the atoms, the single rotating system of the electron adds 1/2 unit to the 1 unit initial level of the double system of the atom. The initial level of the modified specific heat curve is therefore 1 1/2 units instead of the usual 1 unit. This makes the shape of the curve somewhat steeper than that of the initial segment of the normal specific heat curve defined in Chapter 5. The deviation of the thermal conductivity from the constant relation expressed by the Wiedemann-Franz law is the problem with which any theory of thermal conductivity has to deal. And since the explanation derived from the reciprocal system of theory attributes this deviation to the specific heat pattern, the best way to demonstrate the validity of the explanation appears to be to work backward from the measured thermal conductivities, calculate the corresponding theoretical specific heats from equation 11.1, and then compare these calculated specific heats with the theoretical pattern just described. Okay, then he shows a figure that I don't have access to, but figure 17 is a comparison of this kind for the element copper, for which the numerical coefficient of equation 11-1 is 24.0. That's the K over Cp equation, where thermal conductivities are expressed in watts, watts per square centimeter per degree. The solid lines in this diagram represent the specific heat curve applicable to the thermal conductivity of copper as defined in the preceding discussion. For comparison, the first segment of the normal specific heat curve of this element is shown as a dashed line. As in the illustrations of specific heat curves in the preceding chapters, the high temperature extension of the upper segment of the curve is omitted in order to make it possible to show the significant features of the curve more clearly. As the diagram indicates, the specific heats calculated from the measured thermal conductivities follow the theoretical lines within the range of the probable experimental errors, except at the lower and upper ends of the first segment, where transition curves of the usual kind reflect the deviation of the specific heat of the aggregate from that of the individual atoms. Similar data for lead and aluminum are presented also here in figure 18. The pattern followed by the three elements thus far considered may be regarded as the regular behavior, the one to which the largest number of elements conform. No full-scale investigation of the deviations from this basic pattern has yet been undertaken, but an idea of the nature of these deviations can be gained from an examination of the effective specific heat of chromium, which is also here in figure 19, which I also don't have access to. Here, the specific heat and temperature values in the low temperature range have only half the usual magnitude. The negative initial specific heat is negative 1.00 rather than negative 2.00. The temperature of zero specific heat is 16 degrees Kelvin rather than 32 degrees Kelvin, and the initial level of the upper segment of the curve is 2.62 instead of 5.23. This upper segment of the modified curve intersects the upper segment of the normal curve at the Neal point, 311 K, and above this temperature, the effective specific heat of chromium in thermal conductivity follows the regular specific heat pattern defined in Chapter 5. Another kind of deviation from the regular pattern is seen in the curve for antimony. antimony, I'm not sure. Also shown in figure 19. Here, the initial level of the first segment is 0 instead of the usual negative level. The initial level of the second segment is the half-sized value, 2.62. Antimony thus combines the two types of deviation that have been mentioned. As indicated earlier, it has not been yet determined whether any factors other than the resistivity coefficient enter into the constant K of equation 11.1. Resolution of this issue is complicated by the wide margin of uncertainty in the thermal conductivity measurements. The authors of the compilation from which the data used in this work were taken estimate that these values are correct only to within 5 to 10% of the greater part of the temperature range, with some uncertainties as high as 15%. However, the agreement between the plotted points in the figures and the corresponding theoretical curves shows that most of the data represented in these diagrams are more accurate than the foregoing estimates would indicate, except for the aluminum values in the range from 200 to 300 K. In any event, we find that for the majority of the elements included in our preliminary examination, the product of the empirical value of the factor K in equation 11.1 and the temperature coefficient of resistivity is between 0.14 and 0.18. Included are the best known and most thoroughly studied elements: copper, iron, aluminum, silver, etc., and a range of K values extending all the way from 25.8 in silver to 1.1 in antimony. This rather strongly suggests that when all of the disturbing influences, such as impurity effects, are removed, the empirical factor K in equation 11.1 can be replaced by a purely theoretical value K over R, in which a theoretically derived conversion constant K in the neighborhood of 0.15 watts per square centimeter per degree is divided by a theoretically derived coefficient of resistivity. The impurity effects that account for much of the uncertainty in the general run of thermal conductivity measurements are still more prominent at very low temperatures. At least on first consideration, the theoretical development appears to indicate that the thermal conductivity should follow the same kind of a probability curve in the region just above zero temperature as the properties discussed in the preceding chapters. In many cases, however, the measurements show a minimum in the conductivity at some very low temperature, with a rising trend below this level. On the other hand, some of the elements that are available in an extremely pure state show little or no effect of this kind, and follow curves similar to those encountered in the same temperature range during the study of other properties. It is not unlikely that this will prove to be the general rule when more specimens are available in a pure enough state. It should be noted that an ordinary high degree of purity is not enough. As the data compilers point out, the thermal conductivities in this very low temperature region are highly sensitive to small physical and chemical variations of the specimens. Okay, that is the end of chapter 11 on thermoelectric properties. I must admit that that is a chapter that I hardly understand at all. I'm not sure. I've read it, several times before. It hasn't clicked in for me. I'm not, I definitely need to go back and look at it some more before I understand what's going on there. Now, the next chapter is chapter 12, scalar motion. And we will get into that chapter tomorrow. I'm really running short on time here anyway. The power has been out for like the last 4 hours. So I kind of had to stay up to, get my phone charged again and get started and try to get this video out there. But since I finished quite a bit early, I'll just say that we got some great things in store for this channel. We're going to try to wrap up this book, which has many more chapters. Then we're going to look at one of Larson's books on economics called The Road to Permanent Prosperity. And then we're going to look at a number of some of the notes that were taken from Bruce Perret on RS2. Notes that I've taken from him, mainly quotes of forum passages that Bruce used to run 3 different forums on the web, and he made countless numbers of posts over the years on various aspects of RS2, the reciprocal system 2, the re-evaluation of the reciprocal system. Sometimes Perret's work is, really illuminating. Sometimes it is confounding, or even it clouds up the picture, because just when you think you've learned Larson, then Perret comes along and shows that Larson is missing something, and, so he adds another piece that you have to learn in. So sometimes studying Perret can be a double-edged sword, but I do believe that he made some great advances in our understanding of the reciprocal system, and that we need to take those into account, maybe not accept all of them, but take them into account when we weigh our understanding of the reciprocal system along with Dr. Perret's understanding of the of RS2. And unfortunately, Dr. Perret also passed away here back in 2020, so he can't speak for himself, but I'm going to try to do a lot of quoting of him in a lot of those notes. I have several hundred pages of notes from that, and I'll try to kind of organize them at least in a coherent fashion so that we can go over some of those notes as well. And then we will be moving on to a new topic, which I think we're going to move on to some Buckminster Fuller, some synergetic geometry. Look forward to also learning some Ben Iverson on quantum arithmetic. We're going to get into, I believe, some music theory as well. Not only we're going to look at some of my work, my historical work on some really great so-called jazz musicians. And we're going to look at some music theory, look at a little bit of Harry Partch. We're also going to look at, God, I can't even remember the author of the book at this point, but he's the guy that lives out in Texas. The book is called Interference. And Joseph Schillinger on music theory. And yeah, so that might take us all the way through the 2024 year. But I think we're also going to be looking at some ancient history as well. In particular, we're going to look a lot at the writings of Josephus and maybe a few other first century scholars like Suetonius, especially in the context of some of the work of Joseph Atwill. And so that will be something to look forward to. So this channel will be, and I might also start going live here on, I guess, on YouTube and whatever other platform I might end up on, maybe Rumble, and maybe do some live stuff. But great things coming our way. In the meantime, study up on your reciprocal system. We're going to be getting into scalar motion, which we've already learned about a little bit, but scalar motion is so fundamental that it'd be good to hear Larson's chapter here on this topic. And in the meantime, thanks for tuning in. Have a great day.